Hi, Assalamualaikum and good evening. My name is Adam Haris bin Azhar Shaizal and my matrix number is 223305. Today, our group will be presenting about thermodynamics in car engine, internal combustion engine. So, for the introduction, what is the definition of engine? The definition is a machine that converts chemical energy from fuel into mechanical energy. The example is cars, trucks, motorcycles, and other vehicles. The main components are cylinder where combustion occurs, piston where it moves up and down, converting energy into motion, spark plug where it ignites the air-fuel mixture, the crankshaft where it transforms piston motion into rotational motion, and lastly the intake and exhaust valve where it regulates air-fuel mixture entry and waste gas exit. So for the first law of thermodynamics, the meaning of it is the increase in thermal energy of a system equals the work done on the system plus the heat transferred to the system. Another way of stating the law of conservation of energy is increasing in energy equals to the energy added to the system. Next, what is the meaning of internal combustion engines? The meaning of it is the heat engine in a car in which fuel is burned inside the engine or chambers or cylinders. So automobile engines usually consist 4, 6, or 8 cylinders. Each cylinders contains a piston that moves ups and downs, and each movement of the piston is called stroke. So based on this figure, burning fuel in engines cylinders produces thermal energy that is converted into work as the piston move up and down. The crankshaft, transmission, and differential convert the up and down motion of the pistons into rotation of the wheel. So basically, it means that of, when the piston moves up and down, the crankshaft, transmission, and differential converts the motion into rotational motion so that the wheel can move. So next, I'll be explaining about the stroke. So basically, there is 4 types of stroke. The first one is intake stroke, where the intake valve opens as the piston moves downward, drawing a mixture of gasoline and air into the cylinder. The second one, which is the compression stroke, the intake valve closes as the piston moves upward, compressing the full air mixture. The third one, which is the power stroke, a spark plug ignites the fuel air mixture. As the mixture burns, hot gases expand, pushing the piston down. And lastly, the exhaust stroke. As the piston moves up, the exhaust valve opens and the hot gases are pushed out of the cylinder. That's all from me. Thank you.
Hi, I'm the second presenter. My name is Muhammad Raimi bin Romaino. My metric number is 22301. So let's jump to the explanation on fundamental principle of second law of thermodynamics for internal combustion engine. Second law of thermodynamics tells us that energy transformation are not 100% efficient. As you can see from the diagram, when heat is transferred, some energy is always lost as waste heat, increasing the entropy of the system and its surroundings. This principle applies directly to internal combustion engine, which convert chemical energy from fuel into mechanical work. This is Otto cycle, where the internal combustion engine works. First thing you need to know is internal combustion engine operates through 4 main strokes. First is intake, second compression, third is combustion or power, and lastly is exhaust. These strokes work together to convert chemical energy from fuel into mechanical work while expelling waste heat and gases. So let's jump to the diagram. First is intake, and in this process, a fuel mixture enters the cylinder. Second, compression stroke, where the mixture is compressed and the temperature and pressure was increasing. And third is combustion or power stroke. The mixture ignites, pushing the piston and generating work. And lastly is exhaust. where waste gases are expelled, releasing unused energy. This visual demonstrates the energy flow in an internal combustion engine. Out of the 100% energy from fuel, only 25% is converted into useful propulsion. The rest is lost as waste heat 40%, coolant heat 30%, and friction 5%. This energy loss, dictated by the second law of thermodynamics, increases the entropy of the surrounding and limits the efficiency of the engine. Last is the second law also set a theoretical maximum efficiency for any heat engine. This is defined by the Carnot efficiency, which depends on the temperature difference between the hot gases in the engine and the surrounding environment. In reality, internal combustion engines operate far below this limit due to friction, incomplete combustion, and heat losses. So this is the Carnot efficiency formula, 1 minus TL over TH. And example for efficiency for the engine diesel is 0.35 or 35%, and gasoline engine 25% or 0.25.
Hi everyone, today I'll present a thermodynamic analysis of internal combustion engines, focusing on their processes, efficiency, and energy considerations. Internal combustion engines work based on thermodynamic cycles, which is the Otto cycle. The Otto cycle is used in spark ignition engines, like petrol engines, and the diesel cycle, which applies to compression ignition engines such as diesel engines. Each cycle consists of four main stages, which is the first one, intake. Air of the airflow mixture enters the cylinder. The second one is compression. The mixture is compressed, increasing pressure and temperature. And the third one is power. For power, combustion releases energy that pushes the piston down. And the fourth one is exhaust. Waste gases are expelled from the engine. This cycle forms the foundation for engine operation. Now let's look deeper into the thermodynamic processes in the cycle. The first one is isentropic compression. During this phase, the piston compresses the airflow mixture, causing a rise in pressure and temperature. The second one is constant volume, Otto, or constant pressure diesel combustion. Heat is added to the system as the fuel burns, releasing energy. The third one is isentropic expansion. The high pressure gases expand, pushing the piston and producing useful work. And the fourth one is the heat rejection. Finally, the engine expels waste heat during the exhaust phase. The efficiency of these processes depends on the compression ratio given by the formula. Efficiency equal to 1 minus 1 over RC power of gamma minus 1. Moving on to efficiency and energy considerations, heat transfer. Combustion generates significant heat transferred to the engine block and coolant. However, some energy is lost due to friction and exhaust gases. For full air mixture, maintaining the optimal stoichiometric ratio ensures maximum energy output and reduces balance. Entropy analysis, combustion and exhaust processes increase entropy, which represent inefficiencies in the system, such as heat losses and friction. And for energy balance, the engine converts full energy into useful work, but some energy is lost as waste heat or friction. Understanding this balance helps engineers to design more efficient engines. In conclusion, thermodynamic analysis is essential for understanding and improving internal combustion engines. It explains key processes like compression, combustion, heat transfer, and energy loss. Factors such as compression ratio, entropy, and heat transfer play a significant role in determining engine efficiency. By applying these principles, engineers can design engines that are not only more powerful but also more sustainable.